Okay. So now, by the word embedding itself, the definition is very clear. A graph G is said to be embedded on a surface S. So we are considering a graph G, and we say that this graph is embedded on a surface S if it can be drawn in S. So we consider a surface S and a graph G. Now we say that G is embedded on S if we can draw G in S in such a way that the edges of G intersect only at their ends. So we have a surface S. We can embed the graph G in that surface. The condition is the edges of this graph will intersect only at their ends. And what is that graph which intersects only at their ends? It is the planar graph. So planar graph meets one, that is the edges of the planar graph meets only at their ends. So the graph G is said to be embedded on the plane on the surface S. So such a drawing will be called as embedding of G on S. So I will repeat the definition again. Listen carefully. A graph G is said to be embeddable on a surface S if it can be drawn in S so that its edges intersect only at their ends in such a way that the drawing is called an embedding of G on S. Now we shall see one example for this. Now we shall consider the figure K5. K5 is what? It is a complete graph with 5 vertices. So if I consider a complete graph with 5 vertices, so if you see, all the edges will be connected to one another. So only the left out is this. We can connect it like this. And we can see that the graph is a planar graph. So the edges of this graph intersect only at the vertices, okay, at their ends. Now this graph can be embedded on a Mobius band. So the Mobius band is represented as a rectangle actually. So now we are going to embed this graph in a rectangle. So you could imagine this as a 3D actually. This will not touch this line. Okay. So the planarity of this will not be disturbed. So we are embedding this graph in a Mobius band. So such an embedding of K5. So this is K5, the graph K5 is embedded on the surface S. So S is here Mobius band that we are considering. So this is, we say that K5 is embedded on the surface S. So this is the embedding of a graph K5 on the surface S. Okay. So now we saw the definition of embedding. So next we shall move on to a theorem. Okay. A graph G is embeddable in the plane if and only if it is embeddable on the sphere. So if we consider a graph G, so the theorem states that a graph G, so we are considering a graph G. This graph is said to be embeddable in the plane. So this graph is said to be embeddable in the plane if and only if this graph G is embeddable on the sphere. So when it is sphere, we will be having stereographic projection, which you would have already learned in your complex analysis about stereographic projections. Now a graph G is embeddable in the plane if and only if the graph G is embeddable on the sphere. Now we shall prove this theorem. So first, we shall consider a graph G which is embeddable on the plane. So a graph G is embeddable in the plane. So if G is embeddable in the plane, so G will have an embedding G bar on the sphere S. So that let G have an embedding G bar on the sphere S. So you could imagine it three-dimensionally actually. Consider a plane and a sphere. Now if G is embeddable in the plane, it will have a graph G bar. G bar is the graph where the adjacent vertices of G will become non-adjacent and the non-adjacent vertices of G will become adjacent. So if G is embeddable in the plane, then G will have an embedding G bar on the sphere S. Now let us choose a point Z of the sphere which is not in G bar. Okay, so let Z be a point. So let Z be a point of the sphere which is not in G bar. So then what will happen? The image of G bar under the stereographic projection. So image of G bar under stereographic projection from Z will be an embedding of G. Okay. So you could imagine that stereographic projection, the plane. So now we consider a point Z of the sphere which is not in G bar. Okay. So what will happen then if Z is not in G bar, Z will be an element of G. So the image of G bar under stereographic projection from Z will be embedded in G. Okay. Of G will be embedded in the plane. Because Z is not in G bar, it has to be there in G and therefore G will be embedded in the plane. Okay. So I think you have got this. Now we shall prove the converse part. So that is the converse is we have to assume that. The converse part is we have to assume that G is embeddable on the sphere. So if G is embeddable on the sphere, it will imply that a point Z is an embedding of G in S under stereographic projection. As per this data, which I have already told you, Z will be embedded. This is an embedding of G. So Z will be an embedding of G in S under this projection. Okay, under stereographic projection. So if the Z is an embedding, then what will happen? Z is an element of G. Already we saw that. So that will imply that G will have an embedding G bar on S. So therefore, it will imply that G will be embedded on the plane. So G will be embeddable on the plane. So hope you have understood it. So first we consider the theorem states that a graph G is embeddable in the plane if and only if G is embeddable on the sphere. So in order to prove that, first we consider that G is embeddable in the plane. So we take G bar, which is where the adjacent vertices of G will become non-adjacent over here, and the non-adjacent vertices will become adjacent. So that in that G bar, so it will be an embedding on the sphere S. So we consider a point Z of the sphere which is not in G bar. So if it is not there in G bar, it will be there in G, and therefore the image of G bar under the stereographic projection from Z will become an embedding of G in the plane. So hence it will be proved. Similarly, converse, we consider that G is embeddable on the sphere. Now if G is embeddable on the sphere, then we have that arbitrary point Z, which will be an embedding of G in S under stereographic projection, and therefore G will become embedded on the plane. So hope you understood this embedding theorem, and then we shall move on to few more definitions. So next let us learn about dual graphs. So in dual graphs, the first definition we will be learning is phases. Okay, so now what is phases? A plane graph G partitions the rest of the plane into a number of connected regions. So a plane graph, we have to consider a plane graph. So for example, I will consider a plane graph. Okay. Yes, now we shall consider this plane graph and we shall name the vertices V1, V2, V3, V4, and then V5, V6, V7. And this inside we have a vertex which is V8. So these are the vertices and we shall name the edges. This is E1, okay, and then this edge is E2, this is E3, E4, E5, and then this becomes E6, E7, and then this edge let us name it as E8, this is E9, and then we have an edge here, so E10, this edge is E11, okay, and then this is also an edge, we can take it as E12. Okay, so now this graph, if you see, it is a planar graph. Every edges meet only at their end points. So no line is overlapping another line where there is no point of intersection. You could see that this is a planar graph. Now in this a plane graph G, the partitions the rest of the plane into a number of connected regions. Now if you see, this can be partitioned. For example, if I consider V1, V4, V3, V2, it will become one separate partition. Similarly, V1 and then V2 and V3, it becomes another one partition. And then I have another partition here, V6 and V5. So if I consider these two vertices alone, there is another one partition. Similarly, V7, V6 and V5 is one partition. So this plane graph is partitioned into several number of planes. So connected regions on, and if you see, everything will be connected. So the closures of these regions are called the faces of G. For example, now V1, V2, V3, V4 is one connected region. So that partition you can represent it as phase 1. Similarly, V1, V2 and V3, it is also a connected region. We can name it another one F2 for this. Okay. So now similarly, if you come here, this region V6, V5 and this there is the edge E8 and E7, this forms one region, so it can be named as F3. And similarly, V7, V6, V5 forms another region, F4. Now this is a small region, F5. Okay, so like this we have several regions, and after we finish this graph, the outer region is also it is a connected region, so we can name it as F6. So this is called the faces. So a plane graph, this graph has 6 faces actually. So the faces are F1, F2, F3, F4, F5 and F6. There are 6 faces for this graph. So in the faces, the definition is a plane graph G partitions the rest of the plane into a number of connected regions. The closures of these regions are called the faces of G. Now, the set of faces, that is, the faces can be put into a common set, which is capital F of G. So this represents the set of faces of G. And then we have phi of G. So this represents the number of faces. Now, how many faces this graph is having? How many faces are there for this graph, girls?
6 faces. 6 faces.
Yes. Because they are having 6 faces, for this graph, phi of G is equals to 6. Okay. So that is what. Next one, we shall see the definition of exterior face. So when do we say that? The definition of exterior face. Each plane graph exactly has one unbounded face called the exterior face. Now, if you see, the face 1 is bounded. It is bounded by what are the vertices which bound the face 1? V1, V2, V3, V4. These 4 vertices bounds the face 1. Now for phase 2, V1, V2 and V3. This forms a bound. So there is a bound for phase 2. Similarly for phase 3, phase 4, phase 5, we have the bounds. But what about phase 6? Is there any bound for it? No. There is no bound. It is unbounded. So the exterior face is the face which will be unbounded. Therefore, for this diagram, the exterior face is, so exterior face is the face which is unbounded. So here F6 is unbounded. So that becomes the exterior face. Have you understood the definition of exterior face and exterior face?
Ma'am, I
Yes,
have a
ma'am.
doubt, ma'am.
Yeah, tell me.
Ma'am, why is V4 and V5 not a face, ma'am?
V4, where is V4? It's here. V4 and V5. Because, no, actually that face is only F6. But it's not bounded. Are you able to follow? It's
Yes,
not
ma'am.
bounded, yeah. If suppose, for example, if we had a vertex here and if it is like this, then F6 will become bounded and this will be some other vertex V8. Okay. Now F6 is bounded. Now we will say that V4, V5 and V8 has a face. Then if this is F6, there will be some other face outer to this F7 which will be unbounded. So for all planar graph, there will be an unbounded face definitely.
Okay, ma'am.
Yes. So now these two definitions are over. Next we shall see the definition of block. Okay. So a block is a connected graph without cut vertices. So the other day I taught you what is cut vertices. For example, cut vertices are those vertices which make the graph disconnected. For example, so if this is a graph G, and if we remove this vertex, so if we remove this vertex, the edges that is incident with this vertex will also be removed. So what will happen to this graph? It will become like this. Now this edge and this edge and this edge will be removed, and the graph will become like this. So what happens? This was a connected graph, okay, but it became disconnected because of the removal of this one vertex. So this is a cut vertex of this graph. So this is the meaning for cut vertices. Now a block is a connected graph without cut vertices. That is, a block is a non-separable graph. You won't be able to separate it. So it is a connected graph without cut vertices. For example, now we shall consider the graph G. So let's consider this graph. There is a vertex here. So it's a loop. So we are considering a disconnected graph. Yes. So now we are considering a graph G which is disconnected. Now what will be the blocks of G in this graph? So this is a graph G. So the blocks of G will be if I draw this, you will know the difference. So this was the vertex which was already there in that. Okay. But this edge has been removed. So these are the blocks. You could see that none of the edges will be left out. All the edges will remain, but only the thing is, it will be just disconnected. That is it. Yes. Now if you compare the previous graph and this, you will know. All the edges exist. So if you see, none of the edges would have gone, but the graph will be disconnected. So these are the blocks of G. So we have a corollary considering this. The corollary says that every critical graph is a block. So every critical graph is a block. Now let us prove this. So first let us consider a critical graph. So let G be a critical graph. Now we have to prove that this G is a block. So for that we should have a cut vertex. So let that cut vertex be V. So let V be a cut vertex. Then what will happen? The singleton set V is a cut vertex which is also a click. Because in click we saw that like all those vertices which are adjacent to one another, if one of the vertex is removed, they will become non-adjacent. So then this vertex V, which is a vertex cut, will also be a click. But we already have a theorem where we have no critical graph has a vertex cut. Okay, we know that. Has a vertex cut. So this implies if there is no vertex cut, then it will imply that the graph G is a block. Therefore, block is a connected graph without cut vertices. Because of that, G becomes a block. Okay. Yes, you can stop the recording now.